Hi, and welcome to this small lecture in the definition of stress. Anyway, before we begin, let's try to look at a rigid body that's in complete equilibrium. That means we are actually supposing that we don't have any rigid body motions. So let me try to sketch one for you. This body might be subjected to point forces. It might be subjected to gravity, and it has a weight. It might be subjected to surface tractions like this. Anyway, if we want to look inside the body and look at the stress inside the body due to these floats, let's try to sketch it up once more and look at a small area inside. Let's call this one delta A. So that's a small area. On this small area, we might have a resultant force. Let's call this one delta F, and we have a unit normal vector n on this delta A. That means if we want to define the stress or traction vector on this small area, we also need a coordinate system. So let's try to say that this is x, y, and z. On this coordinate system, we have some unit vectors. We could call them E1, E2, and E3. Missed the one here. Going on to the stress, or also sometimes called traction vector, it's actually defined as a vector that's a function of position in the body and also a function of the unit normal vector on that current plane we're looking at. That means on the delta A. That's equivalent to the limit of delta A going towards 0 of delta F over delta A. If we in a special case imagine that we have those three three normal planes, delta A, coincide with the normal axes E1, E2, and E3. We can write the traction vector as follows. And I'm going to index them 1 because it's on the first surface. Still a function of position in the body, where the unit normal vector is now the same as E1 on the x-axis as we had done here. We can now write it as the normal stress times the unit vector plus the shear stress plus the shear stress oriented in the z direction. Furthermore, on the second plane, still a function of position, and the normal vector is now oriented along the second plane, or second direction. It's equivalent to the shear stress in the y-x direction plus the normal stress in the y direction and the shear stress oriented in the z direction. And the last one, Also the shear stress oriented in the x direction, shear stress oriented in the y direction, plus the normal stress in the z direction. Okay, these traction vectors can actually be kind of assembled in the stress tensor, which is a second order tensor. That means it has 9 components. So let me try to write that one. I and J. This is also called the Cauchy stress tensor. Let me write this for you. It can also be shown, but not done here, that it actually only has 6 individual components. That means tau zx is equivalent to tau xz, tau zy is equivalent to tau yz, and so on. If you look at the stress cube, which we could actually make from this sketch out here, and sketch it up, we will see that where the individual stress components are actually located. That means in this direction, according to our coordinate system, we have sigma x. In this direction, we have sigma z. And in this direction, we have sigma y. On the x-plane, we have 2 shear stresses. We have this one, which is called tau x, because it's on the x-plane in the y direction. And we have one in this direction, also on the x-plane, but in the z direction. On the opposite side, we have the shear stress on the z-plane in the x direction, and we have the shear stress on the z-plane in the y direction. The last plane up here, we have the shear stress on the y-plane in the z direction, and we have the shear stress on the y-plane in the x direction. That sums up this small lecture. Thank you.